Hey, I guess you knew this was going to happen. We want to find the equation of a line, right? We're doing all these geometry things, like I said in the first presentation, that we do in coordinate geometry, for example. So the equation of a line and applying vectors, have a look at this one. There's a 3D drawing here. It might give you some idea of what we're trying to do here in describing the equation of the line, that red thing there, so that these points, these general points M, X, Y, Z, lie on that line. How might we do that with vectors? Well, we're going to have a look at that in a minute, but come over here. Here's X-ray my vector, our little plane back again. And I guess a pilot is not too good about vectors. Going through a fairly rocky stage there. Would have been better to get the flight path a bit better than that. I hope they're listening to this vector presentation. Maybe avoid some of that dangerous weather. And over here, I don't think these guys know much about vectors at all. They're going to have a collision here any minute now. So there's vectors for everybody. If you're flying a plane, rowing a boat, you need vectors, mate. Let's come down and have a look at the equation of a line then and see what it looks like in vector land. First of all, I'm going to ask you, what's the equation of a line mean to you? Oh, better think about that. Okay, got any suggestions? Right, well, I guess the most common answer to that is y equals mx plus c, which is in coordinate geometry land. Coordinate geometry, y equals mx plus c. You remember that? M's the slope or gradient, C's the y-intercept. And then you can have the general form. Ax plus by equals big C there. Okay, all of that stuff. But can we generalise it a bit more? What's it really mean? Okay, you might pause the presentation to discuss this in the group and see what you think. What's the equation of a line really mean? And these are examples. But what are the meaning of these two here? I don't know. Might think about that. Okay. Let's have a look then at what the answer is. The answer is a rule which all points must obey if they're to be on the line. That's true about any equations though. Equation of a curve, a circle. It's the rule which all points must obey if they are to be on that particular shape. Alright, have you got your head around that? So we're going to try to describe a rule in vector land so that we can detect whether points line up. Okay, let's have a look then. Okay, here's a couple of diagrams for you. Over here we've got 2D. Okay, just a flat surface as before. And over here we've got 3D. Alright, let's have a look at the 2D case to start with. What we're trying to describe is the rule that point R must obey if it's to lie on this particular line. And the particular line here is through A and with a direction of vector B. Okay, so what would we say? Let's describe point R here by, well, let's say what's the vector needed to get out there? Vector R would be the same as, so going from the origin out to the point, so what do we got to do? Travel to the fixed point, so that's A as a vector, plus so many lots of B, depending on how far away R is on the line. Now R is a variable point, isn't it? Any point. So let's call it T lots of B. Okay, where T is a real number. So T could be any real number. So you could have 2 lots of B necessary to get out to point R, or 3 lots of B. Do you get it? We think of R, and this is explicitly mentioned in the syllabus, this form. R is the resultant vector, if you like, to get out, R for resultant, to get out to any point. So you're going to go to a fixed point with a vector, so you're going to move to A with the position vector A, and then a certain number of multiples, could be fractions, could be negatives, we'll have a look at that in a minute, of the direction vector. So we're thinking about displacing A to any point on that line. And that must be the rule. That would work, wouldn't it? Because they must all be in the same direction here, B. but different lots of B. Do you want to do it over here in 3D land now? Come over here. Well, we think about this general point on the line as being reachable, so we'll call this as R. You go out to a fixed point with A, and then T lots of, or K lots of, the position vector. Here they've used V. We, in the syllabus, will use B because they like the idea of all of them being R equals A plus TB. Using bold for RA and B, but we use arrows because we can't write bold very well. Now, do you get it? Now, that's a neat way, isn't it? If we had this rule, we could generate points on the line if we knew the direction vector and the position vector of any point. This could be any point on the line. We travel out to the line, and then we travel along it with T lots of B. And as we vary T, can you see we're going to specify a particular M. So if T is 1, we'll go 1 lot of B out along this line, and that will give us the first point, M1, let's say. If we made T 1.5, that'd give us another point. Oh, we would be generating an infinite number of points on that line, as long as they follow the rule. Oh, that's the equation of the line. Okay, so let's see what's involved in doing that now. Come down a little bit here, and here's the diagram again. And so we've just been talking about this one over here. What's this saying? And these screen clippings are going to come from two sources in this presentation, Pearson's and Hayes and Harris publications. So if we have a vector V, the direction vector, so we're going to call this the direction vector of the line, because we need to know how to head off down the line, and it's usually within this syllabus denoted B, because they've chosen to do that. Remember now, the resultant vector to get to a point on the line, travel out to any point from the origin, so it's a position vector of any point on the line, plus T times that, the direction vector. That heads us off. Not only do we know we're on the line, but we're heading off in the right direction along it. So we could go 3 lots of B or V, 6 lots. Oh, we could go the other way. Remember, because a line L exists in both directions. That's what we want. And we could do fractions. So T is a member of R, and that means all that R means. Positive, negatives, fractions, decimals, rational, irrational numbers there. Okay. So do you get the idea? It's a powerful way of thinking about a line in vector land. Okay. Come down. And let's have a look at a summary of just what we've been doing there. So this is all you need to know here. This is very, very important because this is the way the IB specify the line. And I suppose we should come over here and just say, well, usually we call the direction vector B. Just reinforcing it now. How do you describe where any point is? Well, you need to know any point on the line. You'll travel out. So this will be a vector to travel out to A. It'll be easy to work out because if A is the point A1, A2, A3, we said in the earlier presentations that the vector would be the same components because you're travelling from the origin. Just check that. OA is A1 take O, A2 take O, A3 take O, 0. I should be saying there. Okay, so do you agree? To get out to point M, which would be from the origin, the position vector x, y, z, that would be the resultant vector of going out to a point on the line, okay, plus T times, this is the direction of the line, the direction vector. Okay, and you must be on it, so it's T lots of direction vector B. That's what we're doing. A fairly simple notion. Okay, so having a look at this, this is a graphical summary. Any point A on the line, we travel out to it, so it becomes the vector A1, A2, A3, travel out, and then travel t lots of b, and we will generate all points on the line by doing that process. Quite a different way of thinking, isn't it? This idea of vectors and displacements. Well, do you get the idea of a displacement? Come down here a bit. Have a look what we've got here. These are called parametric equations, and they're a little bit more explicit statement of how to get points on the line. Because let's have a look at what we've done here. Well, we have to go back up a bit again now. Sorry, I went too far. We're saying the x will equal a1 plus t b1. We've done this before, and the y will be a2 a2 plus t lots of b2. Z will be a3 plus t lots of b3. Okay, parametric equations. What's that saying? Well, you can think of the x of your point on the line as the x value of the given point displaced t lots of the b, which is the x displacement of your direction vector, isn't it? Going back to the idea of displacement of a point. So you can think of it like that. Okay, we're displacing, moving this point along the direction of the line by various multiples in either direction, positive or negative. Remember down here now, t is member of R. Okay, called the parameter. And a parameter in a system means another property of the system. So the property of the system here that we're talking about is t is representing the multiples of b, or fractions, whatever, multiples of the direction vector needed to get to a point. Okay, so each point has got its specific t. You could think of t as this is a Huttyism though, as the growth factor. That's a Huttyism, the growth factor of the line. How much does the line grow in either direction in terms of lots of b? Okay, to get to a point, it's a growth factor of the line. Do you get it? So the take-home message here is if you wanted to generate a point, you might use those. If you want the general pattern, you use this. So what do we call these two? This is called the vector equation of the line, the complete statement of what's going on, and these are called the parametric equations of the line, and they have their usefulness, both of them. Okay, let's have a look at what we can do with them. And first of all though, I'm going to flash back to 2 dimensions. Okay, just make sure you can do the same thing, same idea in 2 dimensions, isn't it? Haven't got the parametric equations here, so I'm going to write them in now. Okay, the parametric equations would be these. They describe the exact x, y and z of any point on the line if we know a particular t. Remember, lock in t, you lock in a particular point on the line. T is your growth factor, your generator of successive points on the line. Okay, there's a notion for you. I'm going now to Hayes and Harris publications and going to look at using this now. A line passes through the point A15, has direction vector 3, 2. Describe the line using a vector equation, parametric equations, and this is not in the course, not going to go there. Okay, so the vector equation, that I be like this statement, so put it down. Resultant vector, to get to a point, you travel out from the origin to the point. So for points 1, 5, you'd use a vector 1, 5, and the direction vector is 3, 2. So lock it in, x, y equals 1, 5, travel out the point, plus t times direction vector, where t is any real number. Okay, what does that mean? Well, the x value is x moved from or displaced from A out t lots of, the movement in the x is 3. The y value is sort of a displacement of the y value at point A, t lots of 2. Okay, so there they are. you can look at this if you like. It's rearranging to get an expression for t so we can get the Cartesian equation. That's not required in this course, but have a look at it. All right, let's go down and look at another one. Here's another one. This is in 3D. Same idea though. We've got a point. This time the direction vector is specified in terms of unit vectors along the axes I, j, k. Must be flexible in your notation here. Write down the resultant vector for a point, travel out to a position vector of any point on the line plus t times the direction vector. So let's have a look now and have a look here. R therefore is x, y, z. Travel out to the point 1, neg 2, 3 from the origin. It will be the same set of components because you're coming from the origin plus t times the direction vector. So that means the x of any point follows the pattern displace the y by t lots of 4, displace the displace the y by, there it is, t lots of 5 in the y direction, displace the z, there it is, by neg 6, t lots of neg 6 in the z direction. Okay, you get the idea there. Alright, let's keep going, have a look. Here's another one. Find parametric equations of the line through 2 points. A couple of questions arise here. Well, they've said it, we don't have a direction vector. So you could have A, B or BA. So you've got to seek your direction vector out first. There it is there. Okay. Now, I'd like to go, they've gone to parametric equations. I think you should go to a vector equation first. Let's do it both ways. Let's have a look at the parametric equations. It's saying that any point on the line can be considered, let's use A for a start, as t2 and plus t lots of the direction vector. So you're going to displace that x from A, t lots of neg 3, there it is there. The y value from A is, sorry, that's not the y value, here's the y value from A, is neg 1 plus t lots of the displacement vector or the direction vector is 1. Then we're going to take the y value from A and displace it t lots of direction vector neg 2. Okay, or you could use point B, alright? There's not a unique equation here because you could think of moving B out various distances along the direction vector, and you should, in any problem, if you're using different starting points, use different parameters here. Why? Let's have a look at it. Let's have a look. There's point A, let's say, and you're trying to suggest how to get to this point on the end here, x, y, z. If you use A and you're going your direction vector, so you travel out to A, then to get to that point it might be t lots of B. But if you start down here somewhere with B, you travel out to B, oh yeah, we won't put B because it's going to get confusing. And now can you see that to get to the same point you'll have different multiples or different amounts of the direction vector B, so we call that SB. Okay, so that's an idea. Let's have a look at it up here. I'd like to put in here using A, what's the resultant vector written as a vector equation. It's travel out to A from the origin, so it's going to be that, plus t times the direction vector. It's not a bad idea to do that first. R equals t plus A, R equals A plus TB. That's using A. If we use B, to get to that point, go out to B from the origin, so it's still going to be the same coordinates as this, from O to B, to travel out. There's a vector, plus t times the direction. Now I've just made a mistake. I'm just trying to explain why you don't do that. So here we would say S times neg1, 0, 2. Using point B and recognising if I'm starting at a different point on the line, the same point further out will be different lots of the direction vector. Why come down here? Because A and B are different positions on the line. So to get to any point, you must use different amounts, different multiples, if you like, of the direction vector. Do you get it? Okay. So now it's your turn to practice now. I've got to do some work now, mate. So let's have a look at these. These problems are from Pearson's. I'm going to show you the complete solutions in a minute. Okay, we'll pause the presentation. I want you to check back, and you should be able to do these 4. I'll bring the other 2 up. Just remembering always with the IB, you must use a column vector for any vectors here. Okay, do not put them down as a line or horizontal vector or, row vector. Alright, so question 5 and 6, have a look at that. Okay, just remember now, vectors which are parallel are k times each other, so it doesn't really matter. If you want the direction of a line, you can use the same components. Let's have a look at the solutions now. Okay, there's question 1. Check your answers there. Question 2. Question 3. Question 4. And I think we just squeeze 5 and 6 in down the end here. Okay, 5 and 6 down the end. Getting the hang of it now? Let's move on, because this builds up into some interesting applications later on. Okay, so let's have a look at relationships between lines now. Can you see the journey we're doing? I promised you in the first presentation to look at vectors in a geometry way and give you an alternative form of geometry, and it's a powerful one, and I hope you're liking it as much, or I would say more, than coordinate geometry. It's much easier. Okay, let's do 2 dimensions. What can the relationship between lines be in 2 dimensions? Well, they could be intersecting, they could be parallel, or they could be coincident. In other words, they would have the same direction vector, right, but instead of being parallel, find a point on one, sub it into the other equation, it will satisfy that as well. In other words, the 2 lines lie on top of each other, coincident, coincide at all points, if you like. So there would be infinite many solutions. They would all the points on one line would obey the equation of the other one, and here they would not meet. Here there would be one point of intersection, a unique solution, if you're trying to find where the lines intersect. Now we're going to do this in 2 dimensions and 3 dimensions, so let's have a look. In 3 dimensions, a little bit harder, because you can have lines which are coplanar. Okay, they're in the same plane. Here's an example here, and they actually have a point of intersection. You could have 2 lines which are in different planes, they're parallel. Or you could have 2 lines in the same plane, sort of saying that this one is the same plane, this one's in another plane, they lie underneath. That sort of idea. But if they are not coplanar, then see, this is in one plane and the red line is going underneath it. So although it looks as if they might intersect, they can't. They are in different planes. They're not coplanar. Different planes. Okay, so they're the 3 conditions now for a 3D case. And what we want to do, and we particularly would be interested in this, if we were flying a plane, or different plane, X-ray Mike Victor, that little one, we would be interested, wouldn't we, if we were on a flight path here with a big jet coming in here, and we got our little plane down here, X-ray Mike Victor. We want to know, are these 2 on the same planes? Are they going to intersect, or have they got the legal amount of separation between the planes? Okay, between the planes, on different planes. What? Too many planes. Okay, let's go down and have a look. So here is an example. This one is from Hayes and Harris publications. So we're looking at 2 dimensions here. Okay, something like boats sailing at sea. Line 1 has this vector equation. Go to that point, displace at S. Notice here, if you're using 2 different parameters, if you're using 2 different lines, you should use 2 different expressions for that parameter. Of the multiple of the direction vector you have to go out, or the growth factor of the line, because you don't want to say these lines necessarily have to grow in the same ratio or same amount of the direction vector, do you? So any 2 problems, you must use different letters, different scalar values for your parameters of growth of each line. Okay, so where would the lines meet? Well, you could say when the vector equations were equal. Let's do it. Neg2 plus s times 3 must equal, this is the, what are these? These are the x values must be the same. Because you could have said it differently here. You could have said in line 1, x equals neg2 plus 3s. In line 2, x equals 15 take 4t. And those must be equal if they're going to intersect. Okay, so like that. And then the y's, you could do parametric equation. Y in equation 1 is 1 plus 2s. Y in equation 2 is 5 plus t. And the 2 y's must equal each other. Okay, so what are you going to come up with? Here they are. 2 equations in 2 unknowns. If it's in paper 1, you have to solve these. We're lucky here they've both got, no, we haven't got 4t in the second one, so we're going to have to multiply that equation by 4, line it up, and then add equations, because that will go out. Get that s is 3, sub it back, and get t is 2. And then just check, this is check what the point of intersection is. So put s is 3 in line 2, and t is 4. S is 3 and t is 2, and in line 1 and 2, wherever they belong, and just check that you do get the same position vector. Notice you'll have a vector here, because remember xy is the resultant vector to get out to the point. So that this will be 7, 7, which means that's the resultant vector from O. Remember, travelling from O, so the lines meet at 7, 7. Okay, I want you to see the subtlety there. It's a very important concept, though, that the vector 7, 7 is from the origin, because that's how we designed our equations there. All right, have a go at some in a minute. Just do another one. It's 3 dimensions now. So we will have these equations. Are you good enough to see the direction vector of this line? Can you remember? It's this last set of values here, the displacement. So B for this line, just a side issue here, will be 2, neg 2 and 4. And A going out to the line from the origin would have been neg 1, 1, 1, wouldn't it? Working backwards to the vector equation, which is A plus TB. Okay. Again, we've got T as a parameter in the second one to keep them completely independent of each other. So, show that the lines are parallel but not coincident. Okay, so let's have a look, and they have reconstituted the equation, just like we're saying over here. Can you work out that these are the components of the initial position vector of the point on the line? And so it's got a direction vector 2, neg 2, 4. And the other one, if we do it, was 1 and 0 in the front there and 3. Position vector of a point on the line was that, and the direction vector, neg1, 1 lot of t, and neg2. Right, remember the coefficients of that parameter, because it's a number of lots of the direction vector, is the direction vector of the line. So we've got that. Now, are they parallel? Yes, because that one is twice the components of that one. And here's the rule we've established earlier. If A is KB for some scalar, then A is parallel to B. The lines are parallel. Let's choose any point on the first line, so let's make S equals 0. So that point is neg 1, 1. So, if you now say, okay, what is the equivalent point on the line 2, where y equals t, the y coordinate 1 is the point where t is 1. So the point is 0, 1, 1. So I've just gone and said, let's go to line 2 with y being 1. That means t is 1. And if you put that back up here to generate a point with y as 1, t would be 1. But the other values are 1 and 1. So therefore, the point there is 0, 1, 1, but the point on the first line was neg 1, 1, 1. So the lines are not coincident. So that's what you have to play with. If the lines are parallel, you go and generate any point for any s value or t value on one, and go and check out the equivalent value on the other one. Are they the same? All right, let's go down now, and I've just flicked down there, so let's go back. Oh, that'll do. Okay. Now, let's have a look at these three equations, and we're going to show that line 2 and line 3 intersect, find an angle between them, and show that line 1 and line 3 are skewed. Okay, let's have a look. Line 2 and 3. We're going to use this one and this one. So, the x and y and z values must all be the same. So there are the x values being equal. Okay, and what can we do here? If you're going to put those two, first of all, I should have made them a statement. S, T and U, all different parameter values there. Okay, or different letters for those parameters. Okay, so have a look at that just for the moment there. So just having a look there. So these are the two lines, x's, the two lines, y's. Right, so y is t, neg 1 take u, and the two lines z's are those two. So you're going to get three equations connecting t and u. So if we solve them like in a paper 1, in a paper 2 you could use simultaneous equations under equa on the Casio, for example. So here, putting these under each other, there they are, we could multiply, well, no, we can just add them in here, can't we? If you say here, those, not simultaneous equation, we're the same variable, so we say neg u equals neg 1, and u is 1, and so t is neg 2, subbing it back in there. So now you've got to check over in this equation, though, that those two values of t and u gives you the same solution. Okay, so checking in 1, u is 1, t is neg 2, obeys this equation. Okay, so there is a common solution. You must do this check to make sure that it makes all three equations true, or holds for all three equations. So, okay, so you've got here, if u is 1, line 2 and 3, sub it in to the equations and find the point. So u is 1 is what? This one, subbing it back in there. You can sub it back in there, and you could sub t is neg 2 in this one, and you should get the same point, shouldn't you? Okay, so what are the direction vectors for the line? And we could put that in there, because we are supposed to find the angle between them now. So if you put your u and t value in there. Well, you don't need to. If we go back up to line 2, we've said here this is neg 1, 1 and neg 2, and in line 3 direction vector 2, neg 1 and 3. Okay, so now we can use the dot product. So come down here and let's look at the rest of that. The dot product, because the cos of the angle between the dot product divided by the two lengths, just using these two vectors now, and we can get that to 3 significant figures, 10.9 degrees. Okay, so let's look at the skew approach, line 1 and 3 now. What we're going to try and do is to see if the lines intersect for a start. Okay, so do the lines intersect? We're going to do the same thing, put the x's together, y's together and z's together. So over here we can use these two equations, add them up here, solving these. We've got 2s take 2u, neg 2s plus u, and they've skipped a couple of steps here. Oh, putting it underneath, there it is there. Okay, so then adding the equations, you get u as naught. Okay, so solving them simultaneously, that's easy, otherwise you have to use equa. So if you put u as equal to naught and subbing it back in this one up here, you get 2s equals 2, so s is 1. So now if you check it back in here, put in u as naught and s is 1, we don't get the number 3 here. We don't get that. So there's no simultaneous solution. Therefore the lines don't intersect. Okay, but here we are. We can say the direction vector still of the two lines. So here they're not parallel. Okay, checking that. And they do not intersect and are not parallel, they are skew. Please note, even if lines are like that, skew if you like, you can think of dropping this down and you can still have an angle theta between them. So they could still ask you in this question, what is theta? Okay, and so you would dot these two as we did in the previous one. So although they aren't in the same plane, they don't intersect, we can define an angle between skew lines by saying if we drop line 1 down onto line 2, then it would have a angle between them. Okay, so it is possible to find the angle between skew lines. Let's have a look. There's a lot to absorb there. Let's have a look at what I suggest your approach should be. Looking at lines in 2D or 3D, go through this process. Are they parallel? Check the direction vectors. The direction vector B1 should be some multiple of B2. Okay. Do they intersect? Use the parametric equations. So you get x1 in let's say P plus TQ, and x2 is M plus, these are vectors, sorry, there. Oh no, they're not, sorry, we won't do that. I'm just doing parametrics. So x is M plus SR or something. Okay, and what we've been doing is equating those, finding R and S, checking, okay, and seeing if they intersect. Now if they're not parallel and they don't intersect, they're going to be skew lines. Okay, and you could still find an angle of intersection, but angle between them, sorry, they don't intersect, but an angle between them. So they're in different planes. One's, if you like, is running under the other, underneath the other, something like that. Okay, so that's the idea now. You've got to go through the checklist and actually see what's happening in 3D. All right. Let's have a look at some problems. So these are initially from Pearson's. So we'll just go back up there just for a minute now. No, come back down. Too far. Okay. So there we have it, 7 and 8. And I want you to have a look at having a go at those. I'll show you the fully worked solutions in a minute. Let's go to 9. Okay, and now let's have a look at the solutions. Pearson's have been very kind here, broken up into paper 1 and paper 2. And here we wouldn't use this method on the Casio, we'd use equimode and simultaneous equations if we're in paper 2 to solve these. Okay, we'll leave that bit. Paper 1 type there. Oops, let's go back up. Okay, part B and paper 2, again using ECRA on the calculator. Then paper 1 type, and again the same thing with paper 2, we would use ECRA on the Casio. Then part D, and again on the Casio using simultaneous. Question 8 there, the solutions, 4 parts. Question 9, just a little bit more there for question 9. Have a look at the rest of it in a minute. C. I've got also some extra questions here from Hayes and Harris. Let's have a look at those. A couple of questions in 2D. I couldn't find much in Pearson, so I've got a couple here. You might have a look at this, check it carefully. Different methods here. Might have to draw the triangle ABC. It doesn't have to be on the grid. Just remember A, B, B, C, and that would be AC. Just make sure you get the directions right there. Okay, and same thing here. I think, yeah, you could go OPR again here. Thinking about them. No need to actually, QPR, sorry. So that's not going to do. It has to be in, we'll go like that. Order around the triangle, so you've got PQ, QR and PR. Help you work out which ones to use to get points of intersection. Alright, let's have a look at the answers to those. Just check that you're doing those basic calculations. Let's have a look at another one, this time in 3D. Lots of 3D practice here. Okay. Going through, are they parallel? Do try to check that first. Intersecting and coincident or skew. Okay. In each case, find the measure of the acute angle between them. Alright. So if they're parallel, there's no angle. Intersecting, there could be angle. Just remember, with skew lines, there could be an angle between them, even though they don't intersect at the point. Alright, let's have a look at the answer underneath here. Alright, well I hope you've enjoyed all that, because what we're going to do is make sure planes don't collide and ships don't collide. That's what we're going to do. We're going to extend this to a practical situation with motion of vehicles and so on. So hone up your skills, and I'll catch you in that next presentation. Cheers.